Okay, let's start. Last day, what we have discussed about this character representation. How can we represent the characters? Basically, we just learned about the number representation previously. And in the number representation, we learn how to represent the decimal numbers as well as how to represent decimal numbers and also how to represent the floating point or these fractionals and integers. So we have learned about that. And here in character representation, this is not about the calculations. Now calculation part is over in your syllabus. So related to the number system, you don't have any other calculations. Here in character representation, so we are thinking about just, this is like a table, right? For each character, there is a represented binary. For each character, there is a matching binary. Character 0 is 000. Character 1 is 0001. Likewise, there is a matching binary for each character. So here actually from 0 to 9, the matching binaries are this. So this is similar to the hexadecimal pattern. 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. So likewise, it is toggling. And here 0, 0, 1, 1, the second digit. 0, 0, 0, 0. Then 1, 1, again 0, 0, then 1, 1, again 0, 0, then 0, 0, 0, 0, 1, 1, 1, 1, again 0, 0, 0, 0. But here you have only up to 10 characters, therefore stopping from 00. Then 8 zeros, 8 ones, but you have to stop from here. Actually speaking, so since there are 4 digits or 4 binaries, how many unique characters you can represent? So if there are 4 digits, how many unique characters that you can represent? Yes, can you remember? So say there are 4 digits. So how many unique characters can be represented? Can you remember? If there are 4 digits, there will be 2 to the power 4, like so 16 unique characters. Yes, 16 unique characters will be there. But here we are going to stop from 0 to 9, right? Because these are for decimal numbers. For an example, 793, you can represent using 7 is this, 0, 111, and 96, 9 is 1110, and 6 is, 93, 793 is 3 is 0011. And you are not going to mention any about like, so the base and all here. You don't want to put that because this is a representation. This is not a calculation. In calculation, yes, you need to put the base. But here, this is a representation, so you can forget this. What you're going to do is you are sending this signal. You are sending this signal through a wire. So when you're sending it through the wire, there are different encodings like Manchester encoding. Anyway, you will be sending like this 0, then ones, then again 1, 00, 1, 2 zeros, again double ones. Likewise, you are sending this as a binary signal, or you can send this as a voltage signal. 0 voltage, 5 voltage, 5 voltage, 5 voltage, 5 voltage, 0 voltage, 0 voltage, 5 voltage, 0 voltage, 0 voltage, 5 voltage, 5 voltage. Likewise, you can send this as a voltage signal. Anyway, you are going to signal only 2. You are going to send 2 status only. That is the nature of this character representation. So please write down the heading, character representation, then write down BCD, then please show. So there are 10 symbols, 10 representations in BCD. So these representations show only the digits. So what are the issues? Can represent, please write down these 2 numbers only, 4 digits code, maximum 16 unique codes. Therefore, not enough to represent letters. developed by IBM. Initially, industrial business machines. This company has developed this system. So please write down. Right, then the next representation is EBCDIC. The next representation is EBCDIC, Extended Binary Coded Decimal Interchange Code. That is extension, that is actually an extension of BCD, right? That is an extension of BCD. So same BCD code, but the thing is same system, but here the number of characters, number of bits, so it has increased. So there are 8 bits. So since there are 8 digits, so it is possible to represent 2 to the power 8 unique symbols, which is equal to 256 unique symbols. Extended binary code decimal interchange code can represent 256 symbols, right? Therefore, so the number of characters or number of bits that it can represent is increased. Extended binary coded decimal interchange code. So in this EBCDIC code, it is possible to represent characters. In addition to the numbers, it is possible to represent characters. Here, you can see simple A is represented this way. 8 and 1 in hexa. You see, it is simple A. And here, C and 4, C4 in hexa, it is capital D. So likewise, I have just given some examples. So here, F9 in hexa is number 9. Likewise, different symbols can be represented, not just the characters. It is possible to represent other symbols too. Here, you can see symbols like ampersand, hash, @mark, percentage mark, colon, brackets. These things can be represented. Right? These things can be represented. Okay. So please write down that too. And also, so let me highlight this part and this part both. Okay. Extended binary coded decimal with 8 bits can represent characters, numbers both. Extended binary coded decimal can represent characters and numbers both. And you can see here. The next one is ASCII. EBCDIC was also developed by IBM, and ASCII, American Standard Code for Information Interchange. American Standard Code for Information Interchange, right? American Standard Code for Information Interchange is basically, it's another competitive standard to EBCDIC, but it has only 7 bits. So the 7-bit code can represent 128 characters. The 7-bit code can represent 128 characters. But so there is another version of extended ASCII, extended American Standard Code for Information Interchange, that can represent again 256 characters, because this 128 version is not enough. Anyway, all ASCII, eASCII, MBCS can represent, right? All these can represent English letters and the special symbols only, but there are other languages too. To represent these other languages, Unicode was introduced. Unicode 16-bit has 65,536 symbols, which can represent, right, which can represent almost any language in the world, because it has unique characters to represent that language. And there is another version of Unicode, theoretically, which can represent 4 billion unique symbols, that is 32 Unicode transformation format, UTF-32, UTF-16. So these are some other versions of representation. So only the summary you need to write down, no need to write down everything. ASCII, and ASCII has 7 bits. eASCII has 8 bits. Unicode has 128. Unicode has 65,536, and 32-bit Unicode is having 4 billion unique symbols. Just write the summary, that is enough. Quickly. Right, okay. So these are to represent the characters, right? These methods are to represent the characters. Characters, basically, it has a value. That is true that it has a value. It has a number value or numerical value. But the thing is, we are not doing any kind of calculations using this. Like, we can do small calculations, but the thing is, this is not mainly focusing about the calculation, that not basically focusing about the arithmetic operation. Just for the representation, to write letter, to write text, to write some stuff, maybe to write textual message, create a document, we need these characters. But so the numbers, in the other hand, we need that for calculations like arithmetic operations like addition, division, subtraction, multiplication, like thing, we need these numbers. So there are 3 ways to represent the numbers in computing. There are a few methods of representing the numbers. The first method is called, so please write down the heading, representing numbers. And the first method is called sign and magnitude. Actually, there are 3 basic methods. The first method is called sign and magnitude. In this method, so we can represent both positive and negative, but integers. Integers means whole numbers only. Positive and negative integers. These are for the calculation purpose. The previous characters, we are not using that for calculation purpose. That is just to show the character value, character, letter, or maybe to display that in the screen. That is the maximum. But here in this, we do some calculations like arithmetic addition, multiplication, division. So we need this number data or numerical data. But this numerical data, again, the problem is like there are negative and positive numbers in numerical data. No? The positive values are there, negative values are there. Therefore, there are 2 ways to represent that. The positive values will be started with digit 0. If first digit is 0, like this, if first digit is 0, the value is called positive. The first digit 0 represents a positive. First digit 1 will represent negative. First digit 0 will represent a positive. If first digit is 1 like this, it represents the negative. But the other number or the remaining part, you need to find out the binary representation of that. 10 in binary, 10 divided by 2 is 5 remainder 0. 5 divided by 2 is 2 remainder 0. 2 divided by 2 is 1 remainder 0. So that is 1 0, bottom to top, 1 0 1 0. 1 0 1 0 is 10. You're writing that 1 0 1 0. Then the first bit is the sign. Then the remaining bit or the intermediate bits will be put in 0 just to make it the register size 8. Or register size means the size or number of digits. If you are given an exercise to represent number using sign and magnitude method, So just using 8-bit register or 8-bit memory location. Sign, you need to make it 0 because this is positive. And then the magnitude is 1010. In between that, you have to put zeros to fill in. Negative 10, similarly, you have to put 1 for negative. 1010 is to represent the magnitude, which is 10. And the remaining bits are 0. That is how you represent the negatives. Okay, so please write down this. I'll give few exercises using this. Representing integers is the heading. Under that, you can write this. Then you can show the positive and negative representations. Quickly add this to your note. Today, we have to write a little. Right, let's do some calculations using this now. Right, let's do some calculations using this now. Okay, so these values, can you represent? So please write down this question. Right, represent 34, 127, 127 plus this is positive, this is negative, again positive and 0. Using sign and magnitude, and also use size 8 register. Okay, please send me the answer to the chat. Send the answer to the chat. Represent 34, 127 plus 127 and 0 is in sign and magnitude, and you have to send the answer to send this to, yeah, please send it to chat. Okay. The values that you get is this 34. 34 is 32 plus, that is correct, plus 34 minus 127. It is all ones. Yes, minus 127 is all ones. That is also correct. Yes, plus 127 is the other 0 and all ones. Yes, correct. And then 0. 0 has 2 representations. So one you have mentioned, that is correct. 0 has this positive 0 representation and negative 0 representation. This is a bit odd. Yes, there's a problem. I think you can understand because there's only one 0, no, positive 0 only. Right? Only positive 0 is there. But here you have both options, positive 0, negative 0, both options are there. So that is the nature. So that is a problem of this representation. The maximum you can go is plus 127 in 8-bit. The minimum you can go is minus 127. And there are two zeros also. Actually, the plus and minus ranges you can represent using this equation. If number of bits are 8, then 2 to the power n minus 1 means 8 minus 1 is 7. 2 to the power 7 is 128 minus 1. It is 127. And minus 2 to the power 8 minus 1 again 7. That is 128 minus 1 is 127. So plus 127 to minus 127 is the margin. Plus 127 to minus 127 is the margin. Right? You can represent using this general equation. Right? Then, so small thing that we need to do. What about the calculations? How can we do arithmetic? Right? That is the problem. So that will introduce another problem of this. That is why I'm giving this. Okay, please write down this highlighted text. And can you try to, okay, so let me convert this first. So then the remaining one, like I'll ask you to do the calculations. So let's calculate this one. Plus 37. Plus 37, as you written, this is like plus 37 is 32 plus 4 plus 1. 32 plus 4 is 36 plus 1, 37. Minus 12, minus 1100. Then if you are asked to do the calculation, this one plus this one. So normally what we do is we have to subtract from the first one. 1 minus 0 is 1. 0 minus 0 is 0. 1 minus 1 is 0. 0 minus 1 is minus 1. You can't write like that. 0 minus 1, you can't subtract. Then you are trying to subtract from 0, 0. Again, cannot subtract. Then you are trying to subtract from 1, 0, 0. 1, 0, 0 is 4. 100 is 4. 4 minus 1 is 3. 3 is 1, 1. That is the easier way of writing, right? There are other ways. So I think you can remember how we have done the calculations in decimal. The high part they were calculation kare. So likewise this. So let's say you have to subtract let's say 173 minus 89. How you did the subtraction? මතක් කරලා බලන්න කොහොමද කරේ කියලා. 3න් 9ක් බෑ. 3 minus 9 is not possible. You are bringing 1 from this, then this is 13. 10 එකක් ගේනවා. 10ක් ගෙනාවම මේක 13යි. 13න් 9ක් කීයද කියලා ඊට පස්සේ ලියනවා. 13න් 9ක් 4යි. That is 4. 13 minus 9 is 4. Then the next one. මෙතන 6ක් ඉතිරි. එතකොට 6න් 8ක් බෑ. 16න් 8ක් 8යි. එහෙම තමයි ඔයාලා ලියන්නේ. ඉස්සරහින් එකක් ගන්නවා. එකක් කියන්නේ 10 ගොඩක්. Right? This is how you do. Then here 0 is 84 is the answer. Similarly, you have to do here also. 1 minus 0 is 0. 0 minus 0 is 0. 1 minus 0 is 1. 1 minus 1 is 0. 0 minus 1 is 100. 100 minus 1 is 11. 100 minus 1. 100 minus 11. එහෙම ලියන්න නැත්නම් මෙහෙම පුළුවන්. 0 minus 1 you can't. You bring 1 from this, but you don't have 1s. Here you bring 1 from this. එක එකක් මේකේ ගේනවා කියන්නේ. Here if you are bringing 1, that will become 2. Right? If you are bringing 1 from that 2, this will become 2. 2 minus 1 is 1. Then 2 remain in here. 2 remain, not 2. 2 වලිමුත් එකක් ගත්තනේ. 1 remain in here. 1 minus 0 is 1. That is another way of thinking. I think rather than thinking like that, it is easy to think the whole part and do. So because you can just subtract from 100 minus 1. That is easy. 100 minus 1 is, 100 is 4. Minus 1 will become 3. 3 is 1, 1. That is easy. That 1, 1 is here. That is easy, right? Yeah, that is easy. Anyway, so let's do the remaining calculations now. Then 1, 1 here, then this is 0. And anyway, you have to write this as a positive. So what is the value? Positive here, 1 is 1, 1, 1 plus 16 plus 8, 24. 16 plus 8 is 24. 24 plus 1 is 25. 16 plus 24. 24 plus 1 is 25. That is the total. Okay. Right. So write down this first, then we'll do the other calculations, right? Okay. The conversion and the calculation. Conversion is given here. The calculation is also given here. So please do the calculations and write down this here. So let's see what is the issue here. So one problem is having two kind of zeros, positive 0, negative 0. That is a problem. The next problem is the calculation problem. To identify that, we need to do some calculations. That is what we are doing now. Minus 37 minus 12. Minus 37 minus 12. The answer is this. Minus 37 minus 12. Right. So what did you do? Normally we have to add the numbers, right? But here minus symbol, but we have to add them together because both are minus now. Therefore, we are not going to subtract anything. We are going to add. 1 plus 0 is 1. 0 zeros. 1 plus 1 is 2. 2 කියන එක අපි ලියන්නේ 2 remaining 2 වල 2 ලියන්නේ 1 0 නේ. 2 කියන්නේ 1යි බිංදුව. 2 is 1 0. The remaining 1. 1 plus 1 is again 2. 2 is 1 0. Remaining 1. That 1 will be here. Then 1 plus 0 is 1. So this is minus 49. The decimal value is like just by adding. Then both numbers plus. Similar way you need to add. But now the final digit is positive. This is positive number. For the third one, yes, it is a positive number. Positive. Same number, positive. Then this one. This is minus 25. How minus 25 is taken? So you have to take 37 up, then subtract 12 from that. This උඩින් ලියාගෙන again 12ක් අඩු කරලා හැබැයි උත්තරේ ලියන්න ඕන minus විදිහට. Because this number is large, no? The minus value is large. So, but we can think and do that. But when it comes to the computer, there is no uniformity. That is a main issue. That means when both numbers are plus, you need to add. When both numbers are minus, you need to add. But you need to write the digit, write this digit as, write this digit as minus 1. Right? Why? Because it was to represent this. This is 49 plus 49. So then both are plus, you need to add, but the value is plus. Both are minus also, you need to add, the value is minus. So if a small number is subtracted, you have to write the large number, then subtract small number and write the number in positive way. And when the large number is subtracted, you have to write the large number first and subtract the smaller number, but you need to make this answer negative. Likewise, no uniformity. Adding and subtracting both are there. Adding, subtraction, both are there. Adding, subtraction, both are there. But the thing is, okay, this is how that calculation happens. So both adding, subtraction there, and you have to think when doing this, but the computers don't like this method because there is one negative 0, positive 0 that you can ignore anyway. But adding and subtracting, so actually computers, it doesn't like subtraction. It like only addition. So subtraction is headache kind of, like you need to bring number from forward, then subtract. These things computers are like, it's very difficult to implement hardware to do these things. Hardware වලින් මේවා කරනවා කියන්නේ හරි අමාරුයි. Therefore, computers doesn't like this. Then, okay. So, okay, I have some other calculations also. Let's do that next day. But so main issues are subtraction issue and this negative and positive 0 issue. Positive, negative 0 issue is a main problem. That's issue number 1, 2. Issue number 2 is subtraction issue. Those are the problems in this method, right? Those are the problems in this method. So no need to write down that. And here, so you can write this statement, right? This statement. So the solution is, there's another representation called, this is number 2 actually, another representation called 1's complement representation. Oh, that is 1's complement representation. So first solution is sign and magnitude, but it has 2 problems, negative, positive 0, and also subtraction issue problem. Difficult to subtract and it's difficult to implement hardware. Therefore, the second method is there. So please write down this. So I can explain this as well and also finish this by explaining 2's complement 2. But let's see whether with the time we can do it. But let's see what can be done, because like if you are going to finish this, then there will be problems. Some students are missing today. So some have asked for the recordings. What will happen if I discuss everything, then they might miss the entire lesson. Anyway, so let's try to finish this first. So is there anything difficult? Please let me know, right? Up to here, is there anything unclear or difficult? Yes, is there anything unclear or difficult related to this?
No, sir, it's okay.
Okay. So the remaining part, what we have to discuss is, right, this. We need to discuss about 2's complement. And also we need to do the calculations. Similar calculations we need to do using 1's complement. The 1's complement, the only difference is the positive numbers, no difference. You can write similar to the sign and magnitude method. The positive numbers are similar and you have to write similar way the positive numbers related to this. But the negative numbers you need to invert. Negative numbers you need to invert, and when inverting these negative numbers, so what is here? Let's see, this is positive number 34. The negative number, so this is how you wrote this this positive 127. No? That 127 need to be inverted. That means ones should be replaced by zeros. All ones will be zeros and 0 will be 1. So that is how the negative numbers represent. It's inverted. That is the method. Anyway, there are calculations related to that as well. I'll be further discuss this in next week, because there are some students missing in the class today. If I continue to do this, they might not understand this. Anyway, so please understand this, or take a screenshot of this and write down in your book too. So this is how the positive 10 is represented. And this is how the negative 10. Negative 10 is basically you write the positive 10, then invert. But the negativity, this bit will remain, but the other bits need to be inverted. That is how the ones complement is represented. Just take a screenshot of this and write down in your note. Okay, the remaining part I'll discuss next day, right? Good night.